is where Domain 4 begins, and it starts with the OSI model. Not because network engineers need it, because security professionals need to know exactly where an attack lives in the stack before they can defend against it.
Think of the OSI model as a building with 7 floors. Every network communication starts in the basement, the physical layer, PDU, and rises floor by floor until it reaches the people in the penthouse at the application layer. Attackers can enter at any floor.
The OSI model is defined in ISO IEC 7490-81. It establishes a 7-layer architecture: physical, data link, network, transport, session, presentation, and application. Each layer communicates only with the layers directly adjacent to it.
Here is why this matters for the exam. Every protocol you will study, every attack vector in Domain 4, and every countermeasure maps back to a specific OSI layer. If you know where it lives, you know what controls apply.
Stick around through Scene 6. We map every security protocol and every attack to its exact OSI layer. That is the shortcut that resolves half the Domain 4 questions you will see.
Scene 2 covers the bottom 3 layers: physical, data link, and network. That is where cables, mandatory access control addresses, and routing live, and where some of the most fundamental attacks begin.
Quick intros before we jump in.
Hey, I'm Michael. Honestly, I am hyped for this one.
I'm Nova. I love when the numbers tell a story people miss.
Liam here. I thought I already knew this. I was wrong.
All right, let us jump in.
Here is the bottom of the OSI stack, Layer 1, the physical layer. It defines the electrical, optical, and radio specifications for transmitting raw bits. Cables, fiber optic lines, radio waves, hubs, and repeaters all live here. Security at this layer is physical locks on server rooms, cable management, and RF shielding.
Layer 2 is the data link layer. This is where bits become frames, structured packages with source and destination mandatory access control addresses. Switches operate here, reading mandatory access control addresses to forward frames to the right port. ARP, the Address Resolution Protocol, also lives at this layer.
Layer 2 is an attack-rich environment, Michael. Mandatory access control flooding overwhelms a switch's address table, forcing it into hub mode where all traffic floods every port. ARP poisoning maps a legitimate IP address to an attacker's mandatory access control, enabling man in the middle access at the data link level.
Layer 3 is the network layer, where packets are created and IP addressing begins. Routers operate here, making forwarding decisions based on destination IP addresses. This layer handles logical addressing, routing protocols, and path selection.
IP security, as defined in RFC 4301, operates at Layer 3. It encrypts and authenticates IP packets, which is why IP security VPNs protect traffic regardless of the upper layer protocols being used. IP spoofing and BGP route hijacking are the primary threats at this layer.
A memory anchor. Layer 1 is your physical wire. Layer 2 is your mandatory access control address and switch. Layer 3 is your IP address and router. Bits, frames, packets, that is the PDU sequence going up the stack.
And that PDU naming is testable. Bits at Layer 1, frames at Layer 2, packets at Layer 3.
The exam will ask you to identify what a switch operates on or where IP addressing lives. These 3 layers are the physical and logical foundation of every Domain 4 topic.
Here is where the upper half of the OSI stack begins. Layer 4, the transport layer, TCP, and UDP. Both operate here along with port numbers that identify specific services. For TCP, this layer also provides reliable delivery with flow control and error checking.
TCP's 3-way handshake SYN/SYN/ACK is a transport layer mechanism. SYN flood attacks exploit this handshake by sending thousands of SYN packets without completing the connection, exhausting server resources. Session hijacking also occurs at Layer 4 by predicting TCP sequence numbers. Layer 5 is the session layer. It manages the establishment, maintenance, and termination of sessions between applications. Think of it as the layer that keeps your database connection open across multiple queries. NetBIOS is a classic session layer protocol, NOVA. Layer 6 is the presentation layer. This is where data formatting, encoding, and encryption occur. Secure sockets layer and transport layer security are often mapped here, though in practice transport layer security spans layers 5 and 6. Data format translation between different systems also happens at this layer.
Layer 7 is the application layer, the one users interact with directly. HTTP, HTTPS, domain name system, FTP, SMTP, and SH all operate at Layer 7. Web application firewalls protect Layer 7. Application layer attacks include SQL, injection, cross-site scripting, and domain name system tunneling.
The 4-layer mnemonic I use. All people seem to need data processing, going top to bottom: application, presentation, session, transport, network, data link, physical. Going bottom to top for memorizing the stack order. Please do not throw sausage pizza away.
Pick one mnemonic and stick with it, Michael. The exam tests which layer a protocol operates at, and the mnemonic gives you the layer number fast. Segments at Layer 4, data at Layers 5 through 7, those PDU distinctions are testable.
The TCP IP model predates the OSI model and is what the Internet actually runs on. It has 4 layers. The network access layer corresponds to OSI. Layers 1 and 2, Ethernet, Wi-Fi, and ARP all live here.
The Internet layer maps to OSI Layer 3. IP addressing and routing happen here. ICMP, the protocol used by ping, is an Internet layer protocol. IP itself, IPv4 and IPv6, is the core protocol at this layer.
The transport layer in TCP IP maps directly to OSI Layer 4. TCP and UDP are the 2 protocols here. TCP for reliable, connection-oriented communication, UDP for fast, connectionless communication. Same layer, same protocols as OSI.
The application layer in TCP IP absorbs OSI, layers 5, 6, and 7, HTTP, HTTPS, domain name system, SH, FTP, SMTP. 2. All of these are application layer protocols in TCP IP. This compression is why the 2 models do not align perfectly in terms of layer counts.
The exam distinction is important. The OSI model is a conceptual reference framework for understanding how network communication should work. The TCP IP model describes how it actually works on the Internet. You will see questions that reference both models.
The practical exam tip: when a question says a protocol operates at the network layer and asks about TCP IP, they mean the Internet layer. The naming differs, but the function is the same. Keep both models in your head simultaneously and map the OSI layer number to the TCP IP layer name. A useful picture: Liam, imagine the OSI model on the left and TCP IP on the right. Draw arrows connecting layers. That visual lets you answer any mapping question the exam throws at you without having to derive the relationship from scratch.
Here is the concept that ties together everything we just covered: encapsulation. Each OSI layer wraps the data unit from the layer above with its own header, and in some cases a trailer. The PDU names change as data moves down the stack.
Picture it as Russian nesting dolls. The application creates data. The transport layer wraps it in a TCP or UDP header, adding source port, destination port, and sequence numbers. That is now a segment.
The network layer takes that segment and wraps it in an IP header, adding source IP address and destination IP address. That is now a packet. The router reads the IP header to decide where to send it. Nothing below Layer 3 touches the port numbers in the segment.
The data link layer wraps the packet in a frame header. Hey, adding source and destination mandatory access control addresses, and appends a frame check sequence trailer for error detection. That is now a frame. The frame check sequence lets the receiving end verify the frame arrived intact.
Finally, the physical layer converts the frame into bits, electrical pulses, light pulses, or radio waves depending on the medium. On the receiving end, encapsulation strips each header as data moves back up the stack, layer by layer, until the original application data is restored.
This encapsulation model has direct security implications. When a firewall at layer 3 inspects a packet, it can see IP addresses but not port numbers, that is in the segment header above. A stateful firewall at layer 4 can see port numbers. An application layer proxy sees everything, including the payload.
The exam will test PDU names and encapsulation order. Bits, frames, packets, segments, data that sequence bottom to top is fixed. Know it as automatically as your phone number.
This is where it all connects, security controls mapped precisely to OSI layers. Let us go through the layers from bottom to top. At layer 1, physical. Security is entirely physical, locked wiring closets, fiber optic tapping detection, and RF shielding.
Layer 2 security includes IEE 802.1x for port-based access control. Think of it as a bouncer at the door who checks credentials before a device gets on the network at all. Mandatory access control address filtering and virtual LAN segmentation are also layer 2 controls, though VLANs have known bypass attacks.
Layer 3 is where IP security does its work, encrypting and authenticating at the IP packet level. Access control lists on routers are also a layer 3 control. Packet filtering firewalls that only look at source and destination IP addresses operate here.
At layer 4, stateful firewalls track connection state. They know whether a packet is part of an established TCP session or a new connection attempt. Transport layer security operates partly at layer 4 during the connection phase. Port-based filtering also lives here.
At the application layer, layer 7, we have web application firewalls that inspect HTTP and HTTPS traffic for injection attacks. SSH, HTTPS, SD-MIM for email encryption, and application proxies all operate here. These controls see the full application payload, not just headers.
The cross-domain connection here is powerful. In Domain 3, you studied IP security. In Domain 5, you will see 802.1x for network access control.
In Domain 6, port scanning attacks layer 4, locking in the OSI layer for each protocol now pays dividends through every remaining domain.
Here is the anchor. Forget everything else and lock in this one sequence. Bits at layer 1, frames at layer 2, packets at layer 3, segments at layer 4, data at layers 5 through 7.
That sequence is tested on every network question, and device mapping flows from it. Hub at layer 1, switch at layer 2, router at layer 3.
Device mapping is equally testable. A hub is a dumb repeater at layer 1. A switch is a smart forwarder at layer 2 using mandatory access control addresses. A router is a path selector at layer 3 using IP addresses.
Protocol to layer map in IP security at layer 3, transport layer security spanning 4 through 6, SSH and domain name system at layer 7, ARP at layer 2, ICMP at layer 3.
Attack to layer mapping closes the loop. ARP, poisoning attacks layer 2, IP spoofing attacks layer 3, and SYN floods attack layer 4. Knowing the layer tells you which control to apply.
The OSI model is a Swiss Army knife for exam questions. Any question about where something operates, apply the PDU sequence and the protocol layer mapping you just built. Layer by layer, the answer becomes obvious.
Drop in the comments which OSI layer do you find most confusing, or which protocol layer mapping always trips you up. We read every comment, and the patterns shape what we cover in future videos.
Next up is CISSP 4.2 Network Protocols Deep Dive. We cover TCP versus UDP, IP addressing, domain name system, and DNSSEC, and the Kamensky cache poisoning attack. Read the spec. On the exam.
Okay, it is quiz time. Let's find out what's stuck. Think through each question carefully before you answer.
A like and subscribe takes less time than reading this sentence. Do it now and help us reach more learners.
A security analyst observes that a switch is forwarding all traffic to every port instead of only the intended destination port. Which type of attack most likely caused this behavior? The correct answer is B, mandatory access control flooding. The switch's CAM table was overflowed, forcing it to broadcast all traffic.
At which OSI layer does IP security operate, and what security function does it provide at that layer? The correct answer is B, Layer 3 network. IP security encrypts and authenticates IP packets at the network layer.
Which term describes the Layer 2 protocol data unit, and which device operates primarily at this layer? The correct answer is D, frame. A switch uses mandatory access control addresses to forward frames to the correct port.
Strong work on the quiz. Here is what we locked in today. The OSI model has 7 layers, each with a specific PDU: bits at layer 1, frames at layer 2, packets at layer 3, segments at layer 4, and data at layers 5 through 7. That sequence is foundational to every remaining domain 4 topic.
Device to layer mapping is automatic knowledge now. Hub at layer 1, switch at layer 2, router at layer 3. Firewall type determines which layer it inspects, packet filtering at 3, stateful at 4, application proxy at 7.
The TCP IP model compresses OSI into 4 layers. Network access absorbs layers 1 and 2, internet maps to layer 3, transport stays at layer 4, application absorbs layers 5, 6, and 7. Exam questions will use both model naming conventions. Stay fluent in both.
Security controls map precisely to layers. O2.1x at layer 2, IP security at layer 3, stateful firewalls at layer 4, WAFs and SH at layer 7. Every domain you study from here connects back to an OSI layer and a PDU.
Next video is CISSP 4.2 Network Protocols Deep Dive. We go deep on TCP versus UDP, IPv4 versus IPv6, Domain Name System Security (ARP), and the Kamensky attack. Watch that next video now.
Subscribe and stay with the series. Think in pictures, and the answers follow.
Professor Erica signing off.